Hi everyone. Today you and I will be talking about conformalized survival analysis with adaptive cutoffs. This is a joint work with Rina Barber and Jimei Ren and can be viewed as a generalization of existing work by Candès and Jimei, where they use a fixed cutoff instead of adaptive cutoff. Now, before going into further details, let's look at the problem setup from survival analysis literature. We have X, the covariates, C, the censoring time, and T, our true survival time. But we don't observe true T. Instead, we can only observe T tilde, which is defined as the minimum of T and C, the right-censored survival time. We have our observed data, D, which consists of three tuples, XC and T tilde for n many data points. And given a new test point, X, we want to build a covariate dependent lower predictive bound, in short LPB, for T, which will satisfy the PSE type validity for some level delta comma alpha. This is formally defined in the slides. Now we have X and T tilde, so we can use standard conformal prediction techniques to build a calibrated LPB for T tilde, but that will be very conservative. So in the paper by Candès et al., they use a following technique. Intuitively speaking, if C is large, then T and T tilde are very close. So we can choose a cutoff C0 and extract a working subpopulation where the censoring times are greater than or equal to C0. They also consider a secondary censored outcome, which is minimum of T tilde and C0. And they note that in the working subpopulation, T minimum C0 and T tilde minimum C0 are exactly same. Now we can use T tilde minimum C0 as a proxy for T and build a calibrated LPB for T minimum C0. But the working distribution and the target distributions are very different, although it turns out that only shift in the distribution is through covariate distribution. So we can use standard weighted conformal prediction techniques to tackle this covariate shift problem. But the problem here is we are using a fixed cutoff C0 for every covariate value. So in particular, in some settings where the C and X are very dependent, it might so happen that at some regions our cutoff is very large and some other region our cutoff is very small, leading to unbalanced sample sizes. In particular, if we look at this motivating example where X comes from uniform and C and T are both normal with mu and sigma as written. Here in this setting, C and T have opposite trends with respect to the covariate. And in such a setting, we will see if we use fixed cutoff, then our calibrated LPBs will be very conservative, while choosing adaptive cutoff will solve this issue.
To introduce our method, we begin with a general framework with calibrated lower prediction bounds. Suppose that we're given a parameterized family of LPBs, L hat of V, such that L hat of V is non-increasing in V for any fixed X, and the construction is independent of the calibration set, which can be realized by the data splitting approach. Here, V star is an oracle choice of the threshold, but in practice, we do not have the access to the true distribution, so we need to estimate the miscoverage rate. Here are the two estimates. The first one is the estimate used by the naive conformal prediction, and the second one is adopted by the paper of Candès et al. But here the cutoff C0 is fixed. So in our paper, we propose the miscoverage, the estimate for the miscoverage rate in equation 2.5. Here we can see that L hat of V plays both the role of an adaptive cutoff as well as a candidate LPB to be calibrated. Then V hat can be chosen by the minimum V such that the monotonized estimated miscoverage rate is bounded by alpha.
Talking about the theoretical results, if we assume that the estimated weights are bounded, we can show that our proposed LPB with pessimistic stopping rule will achieve approximate PSE type coverage. The theoretical details are provided in the slide, but roughly speaking, the LPB achieves approximate exact PSE type coverage if either the censoring mechanism or the conditional quantile of T is well estimated.
So in numerical studies, we adopt the data splitting approach, and the candidate set, capital V, is chosen by the knots at which the indicators in the weighted estimate change the signs. And for the choice of L hat of V, the oracle choice is a true conditional quantile. We can also use a plug-in estimate, but as is mentioned in the theorem, a bounded weight is preferred. So we set L hat of V as a minimum of the two quantiles, such that the plug-in weight is upper bounded by log n. Here's the method to compare this. And we go to the setting where C and X are dependent. Here we can see that our method have a nearly exact coverage, but the two methods based on the censored quantile regression is slightly undercovering, and other methods are conservative. And we should notice that the method with a fixed cutoff, which is denoted by QC0 here, has nearly 0 LPB, which is due to the failure in capturing the variability in C given X. Thank you. And if you are interested in more real data analysis, please refer to our paper.